All right. So now we move to complex differential calculus. So we discussed this earlier. We discussed limits. Now we'll discuss continuity. Very simple definition, like what we have, done in real functions. So continuity of a function f of z is said to be continuous at z equal to z naught if limit x tends to z naught f of z is equal to f of z naught. So f is said to be continuous in its domain if it is continuous at each point on its domain. So pretty much the same definition. Then next, let us look at the derivative. So derivative of f at point z naught is defined as, this is f dash z naught is equal to limit x tends to z, delta z tends to 0, f of z naught plus delta z minus f of z naught upon delta z. So the same definition, or f dash z naught is limit f of z minus f of z naught divided by z minus z naught. Okay. So now rules for differentiation. Yeah. So important note, the limit above must exist and approach the same value. Okay, not this is, sorry, the same value, both the same value along any path in which z approaches z naught. Now rules of differentiation, if it's a constant times function, derivative of constant time function is constant comes out times the derivative of the function. Derivative of sum of two functions is equal to sum of their derivatives. And this is UV rule. This is applicable here. Note that, see, f of z may be differentiable, but f of z, f of z bar is not differentiable at any point z. Okay, just because the previous one is differentiable, it is not that this can be differentiable. Next, important definition, very important definition. Is of analytic functions. This is the key definition in differential complex differentiation. Okay. A function f of z is said to be analytic in a domain D if f of z is defined uniquely and is differentiable at all points of D. So at the domain, if it's differentiable at all points D, then it is said to be an analytic function. So function is said to be analytic in a domain D if f of z is defined uniquely and is differentiable at all points of D. So a point at which analytic function ceases, the point at which the analytic function ceases to possess a derivative is called as a singular point. So within the domain, if there is a point at which a function is not differentiable, it is called as a singular point. Real and imaginary parts of analytic functions are called conjugate functions. So these are some definitions. So now let us examine some analytic function. So here example is given, w is equal to log z. So we just follow the derivative the same, dw by dz is equal to 1 upon z. All right. Now at z equal to 1, dw by dz will be equal to 1. Okay. Now we will discuss more on this. Now, how do we know whether a function is analytic or not? Whether a function is analytic or not, it is very important that it satisfies the Cauchy-Riemann equation. Cauchy-Riemann equation. Okay. Okay. So if F is analytic, then U and V satisfy the Cauchy-Riemann equation. What are the Cauchy-Riemann equations? These two are the Cauchy-Riemann equations. Okay. So we'll not go through the proof of the Cauchy, this theorem, but this is how we check whether a function is analytic or not. So let W equal to f of z is equal to u plus iv be defined and be continuous on some neighborhood of z equal to x plus iy and differentiable at z itself. Then at that point, u and v satisfy the Cauchy-Riemann equation. What are the Cauchy-Riemann equations? Dou u by dou x equal to dou v by dou y. Dou u by dou y is equal to minus dou v by dou x. Okay. Thus, if f is analytic in the domain, this is the important point. Thus, if f is analytic in the domain V, then u and v satisfy the Cauchy-Riemann equations at all points of D. So wherever the function is differentiable, at that point, the Cauchy-Riemann equations are satisfied. So if a function is analytic, that means at every point it should satisfy the Cauchy-Riemann equation. The proof for this comes from the fact that analytic function means you can approach through any path. Through any path you can approach and the derivative will be the same. So, okay. Now it is important to note yeah, it is important to know that Cauchy-Riemann equations are both necessary and sufficient condition for a function to be analytic. That means this is what so many questions come in this section, that how to check whether it is analytic or not. So let us do some examples. Now f of z is equal to z cube. Check if f of z is analytic. So let's look at this solution. So f of z is z cube, which is x plus iy the whole cube. So this is x cube plus 3x square iy plus 3x iy the whole square plus iy the whole cube. So we get x cube plus I times 3x square y minus 1, I square is minus 1, 3xy square. Now I cube is minus I. So iy cube. X cube minus 3xy square plus I times 3x square y minus y cube. So this is u and this is v, f of z. Now, let's look what is dou u by dou x. Dou u by dou x is 3x square minus 3y square. Now, dou u by dou y will be minus 3 to 6xy. Next, dou v by dou x, let us see, will be 3 to 6xy, and dou v by dou y will be 3x square minus 3y square. So therefore, we observe that dou u by dou x is equal to dou v by dou y, and dou u by dou y is equal to minus dou v by dou x. See here, dou u by dou y is minus 6xy, dou v by dou x is plus 6xy. So you get a minus sign. But dou u by dou x is equal to dou v by dou y. We get the same. So the Cauchy-Riemann equations are satisfied. Therefore, now this is irrespective of any value. This is for all x comma y belonging to R. For all real values, that means z equal to x plus iy. For any complex point z, this is valid. Therefore, f of z is analytic throughout the domain. The entire domain of complex numbers. Okay. We'll do another one. Now, before we go to another example, if complex function is written in polar form, if complex functions is written in polar form, that is z is equal to r into cos theta plus I sin theta, or this is the Euler form, z equal to e power I theta, and f of z is equal to u of r theta, r comma theta, plus I times v of r comma theta. Then the Cauchy-Riemann equations are dou u by dou r is equal to 1 by r dou v by dou theta. Dou v by dou r is equal to minus 1 by r dou u by dou theta. This 1 by r term comes here. This we have to remember. Okay. Okay, this is an important part. Just a second. Okay. Now, second example. Now, check analyticity of f of z is equal to z square and find df by dz. So if we found for z cube, this is much easier. So f of z is z square, which is x plus iy, the whole square. And this becomes x square minus y square plus I times 2xy. So this is u and this is v. Okay. So now dou u by dou x is 2x and dou u by dou y is minus 2y. Dou v by dou y is equal to 2x and dou v by dou x is equal to 2y. Okay, therefore dou u by dou x is equal to dou v by dou y and dou u by dou y is equal to minus dou v by dou x. Okay. So now what is the derivative? How do you find the derivative? So the derivative will be like this. Df by dz will be, now f is u and v, right? So we can approach keeping y constant. You can approach with respect to x. So then you get ux plus ivx. So in that case, you get derivative with respect to x. If you do, you get 2x plus I times 2y. 2x plus I times 2y, twice of x plus iy, which is 2z, which we can directly write. Or we can approach via another path where x is constant and y. So let's say on this is the z plane. Okay, this is the z plane and some point we are considering. So we can approach here through this path. Okay, keeping y constant, and we are approaching this point z, sorry, this point z along um, along a line parallel to the x-axis. So x is varying, but not y. If we approach this way, then y is constant, but sorry, x is constant, but y is varying. So when we approach that way, then uy plus I v y. Okay, the derivative is like this. I'll just show. The first part is simple. The second part, the second part. I will show this. Um, so see, f dash z is defined as limit x delta z tends to 0, f of z plus delta z minus f of z by delta z. Okay, so we get limit delta z tends to 0. That means both delta x and delta y tend to 0. It means, and this will be u of x plus delta x comma y plus delta y plus I times v x plus delta x comma y plus delta y minus u of x comma y plus I times v of x comma y. So we are just writing this. This is delta x plus I delta y. Now, the first part, now this delta z tends to 0 means delta x tends to 0 and delta y tends to 0. Now in path 1, the first path, first, delta y tends to 0 and then delta x tends to 0. If we do that, you will get f dash z. First, delta y tends to 0. We get limit delta x tends to 0. Apply this, u of x plus delta x comma y, delta y is tending to 0, plus I times v x plus delta x comma y minus u x comma y minus I v x comma y upon delta x. So let us see what happens. We get limit delta x tends to 0. Take the real parts. And then the imaginary part. So when you apply the limit, when you apply the limit, this is dou u by dou x, derivative of u with respect to x plus I times dou v by dou x. So ux plus I vx. This is f dash x. If you take part 2, both should be equal, by the way. First, let delta x tend to 0, then delta y tends to 0. If we do this, then we get f dash z is limit x delta y tending to 0 limit delta y tending to 0, because delta x is already made tending to 0, you get u x into y plus delta y minus u of x comma y by what you get is instead of x plus iy, delta x plus delta y, delta x tends to 0, I get I delta y in the denominator, and I times v of x y plus delta y minus v of x comma y by I delta y. So what we get is 1 by I is minus I. 1 by I is minus I. And this one we get is dou u by dou y plus I cancels plus dou v by dou x. All right. So this is minus I dou v by dou x minus I times dou u by dou y. So these two are equal. This and this should be equal. This is v y, sorry. So from here we get Cauchy-Riemann equations. The real parts should be equal and the imaginary parts should be equal. So that's how we get the Cauchy-Riemann equation. So here, so from first part we did. So the derivative df by dz is either u of x plus ux plus ivx is equal to vy minus I uy. Okay. So now, so first part we found, this part we found. Now let us look at this. What is u? U was x square minus y square. And what was v? 2xy. So derivative of u with respect to y is minus 2y. Derivative of v with respect to y is 2x. Therefore, df by dz is 2x minus I times minus 2y. So you get twice of x plus iy, which is again 2z. So either by this way or the first way, we get the derivative. So remember this part. This is the critical part. Based on Cauchy-Riemann equation, the derivative of a function, which is u plus iv, will be either ux plus ivx or vy minus iui. Okay. Of course, if we keep differentiating, we get directly, if we differentiate, we get the function, the derivative. Next, an important example. Important example. Now check if this is example 3. Check if f of z is equal to z bar, that is x minus iy, is analytic. So we have to check the Cauchy-Riemann equations. So f of z is x minus iy. So this is u and this is v. Now dou u by dou x is equal to 1 and dou u by dou y is equal to 0 and dou v by dou y is equal to -1 and dou v by dou x is equal to 0. So what we observe here, dou u by dou x is not equal to dou v by dou y. Usually these two should be equal. Dou u by dou x should be equal to dou v by dou y. However, this is equal dou u by dou y should be minus dou v by dou x. This is acceptable because both sides are 0. So with minus sign is also. So this is never. It is never possible. Dou u by dou x equal to dou v by dou y. That means at no point the function is differentiable. Therefore, f of z equal to z bar is not analytic. At any point, or not analytic sufficient. Analytic means throughout we talk. So it is not differentiable at any point. Now let's look at example 4. Find the derivative of this. Check for analyticity and find the derivative. Check whether it is analytic or not. So f of z is 1 upon x plus iy, which is x minus iy upon x square plus y square. So we get x upon x square plus y square plus I times minus y upon x square plus y square. So now dou u by dou x, dou u by dou x. So this is u and this is v. So dou u by dou x, when you do, you get, differentiate this partially with respect to x. So denominator square, u by v rule, then x square plus y square times 1 derivative minus x times 2x. So we get minus of x square minus y square by x square plus y square the whole square. Now, dou u by dou y, this will be minus x upon x square plus y square the whole square, because x will be treated as constant now, multiplied by 2y. So minus 2xy upon x square plus y square. Now dou v by dou x, let us take first. Now v is minus y upon x square plus y square. So with respect to x, y is treated as constant. So you get plus y upon x square plus y square the whole square times 2x. So which is 2xy upon x square plus y square the whole square. Now dou v by dou y. Okay, we remember is this. So now u by v rule we have to apply with and differentiate. I'll take this minus sign out, this minus sign out, derivative y, then y times differentiating the denominator with respect to y. So we get minus of x square minus y square upon x square plus y square the whole square. So observe here, this is minus of x square minus y square by x square plus y square whole square. And this is the same. Therefore, dou u by dou x is equal to dou v by dou y. And observe this, dou u by dou y is minus of dou v by dou x. Okay. So these are the Cauchy-Riemann equations are satisfied. So function is analytic, except at one point when x equal to 0 and y equal to 0, the derivatives do not exist because denominator goes to 0. It is not that it is approaching 0, it goes to 0. When you apply the limit, okay, this will go to 0. So because denominator is whole square here, suppose y tends to 0, you will get x square by x power 4, that is 1 by x square, and as x tends to 0, it is infinity, undefined. So except function itself will not be defined there. So that's the problem. Except for z equal to 0 plus I times 0, function is analytic throughout. And the derivative will be just differentiate 1 by minus 1 over z square. You can prove this. You can show that this is ux plus I vx. So from there also we can show this. You can try it later. Okay, you can simplify, but directly we can write. So that's about analytic function. Now one polar form once we have to check. One problem on polar. So whatever we have discussed are important forms, by the way. 1 by z is a very important one. Z bar is another important result to remember. And z square and z cube are simple, fairly simple, easy just to check that. Now, first, if w is log z to the base e, okay, not mentioning base e, but it is base e, find w dw by dz and determine where w is non-analytic. So at which point does Cauchy-Riemann equation not be valid? So we know solution for this is, say, z is e power r e power I theta. And we know that this is r e power I 2k pi plus theta. Okay. Because it repeats itself. You get the same, you get so many numbers. So log z is log r plus I times theta plus 2k pi. Okay. Now w is log r plus I times. Now theta plus 2k pi. Now we will check this. This is u and this is v. Now dou u by dou r is 1 upon r. Dou u by dou theta is 0. Now dou v by dou r is 0 and dou v by dou theta is 1. So what are Cauchy-Riemann equations? Dou u by dou r, dou u by dou r is equal to 1 upon r times dou v by dou theta, and dou v by dou r is 1 upon r dou u by dou theta. So both, because the second term is 0, these are satisfied. So Cauchy-Riemann equations are satisfied. So function is analytic. Now, which points? You just have to see where, at which points will function not exist. When z equal to 0, comma 0, that means your modulus is 0 and amplitude is 0. Amplitude is undefined, in fact. So at that point, 0, comma 0 function doesn't exist. So W is equal to log z is analytic at all points except z equal to 0. So now dou W by dou Z how do we do this? So it is dou U by dou R plus I times dou V by dou R, which is 0. So dou U by dou R is 1 over R. Just a second. Now, this should be 1 over Z. So this is 1 over R if you directly differentiate, you will get this. Okay. The derivative, if we do by that method, it is this one. Derivative is this is the derivative, or it is dou V by dou theta 1 by R minus I times dou U by dou theta e power minus I e theta. This is the definition just by the first principles we do. So this is what is the derivative. When we do by first principles, we can show this. So you get dou W by dou Z is, this is 1 by R to e power I theta, which is 1 over Z. It's 1 over Z. Okay, this is about analytic functions. Next, an important topic. Laplace equation and harmonic functions. Hmm. So if z, f of z is equal to u plus iy is analytical, then u and v satisfy the Laplace equation. What is Laplace equation? It is, del square u equal to 0 and del square v equal to 0. If you remember del, it is now the del operator is a vector function. Now del square is del dot del. We get dou square by dou x square plus dou square by dou y square. So del square u. So Laplace equation is this. So we get del square u by dou square u by dou x square plus dou square u by dou y square equal to 0, and dou square v by dou x square plus dou square v by dou y square is equal to 0. So this is a Laplace equation. And so solution of Laplace equations having continuous second order partial derivatives are called harmonic functions, and their theory is called potential theory. Now applications of Laplace equation is in gravitation, electrostatic, fluid flow, heat conduction, and so on. So you get Laplace equations there. So U and V are called as conjugate harmonics if they satisfy. So conversely, if two functions U and V satisfy Cauchy-Riemann equations in the domain, then they are real and imaginary parts of analytical function, and U and V are said to be conjugate harmonics of each other. So example, verify U is equal to x square minus y square minus y is a harmonic function. And find the conjugate harmonic function of U. So to verify, what do we have to check? We have to check whether if it's a harmonic function, del square U will be 0 if U is harmonic. So what you get is dou U is x square minus y square minus y. So do u by dou x is 2x, and dou square u by dou x square is 2. Dou u by dou y is minus 2y, and dou square u by dou y square is minus 2. Therefore, dou square u by dou x square plus dou square u by dou y square is 2 minus 2 equal to 0. So it is satisfying the Laplace equation. U satisfies the Laplace equation. That is del square u equal to 0. So it is a harmonic function. Therefore, u is harmonic. So u is a harmonic function. Now we have to check how to find the conjugate harmonic. So whenever it's a harmonic function, it satisfies the u and v satisfy Cauchy-Riemann equation. So what you get is dou u by dou x is equal to dou v by dou y, and dou u by dou y is equal to minus dou v by dou x. Therefore, dou v by dou y is, say, dou u by dou x, that is 2x. So which implies integrating v will be 2xy plus some function of x, because partial derivative with respect to y should give you 2x. So this can be a function of x, need not be the constant of integration can be a function of x plus some constant. Now substitute in this. Now dou v by dou x is 2y plus phi dash x. This should be equal to minus of dou u by dou y. Okay, dou v by dou x should be minus of dou u by dou y, which is equal to minus of minus 2y, that is 2y. So yeah. Sorry, this is, so phi dash x equal to 0 we get. Oh, I made a mistake here. I made a mistake. Dou u by dou y, yeah, it's a mistake. It is not, it is minus 2y minus 1. I made this mistake here. So here I should get minus of 2y minus 1 plus 1. So this is equal to 1. So phi of x, integrating with respect to x, you will get x plus a constant c, some constant c. Therefore, v will be 2xy plus x plus some constant c. Okay. So we have found the conjugate harmonic, and f, the analytic function, is u plus iv. which is x square plus y square minus y. Sorry, x square minus y square minus y plus I times 2xy plus x plus c. Okay. Now you can identify the exact terms in terms of z. Ix minus y plus ic. So this is z square. If you take I common, write this as plus I square. This is x plus iy. So this is z square plus iz plus ic. This is the function. So from one function, from u, we could identify one harmonic, we could identify the other harmonic, and we could identify the analytic function also. So let us see if we can do some problems from gate directly. I'll just share. Huh. So let's look at this. There's a direct question. So now the function w equal to u plus iv is half log of x square plus y square plus I times tan y by x. Now, at which point this is not analytic? Now, this is what? If we observe carefully, this is log of under root of x square plus y square plus I times tan inverse y by x is theta, basically. So I'll write that. So this is log r plus I theta. So this is log of r e power I theta. So this is log z, and we know that log z is not analytic at 0, 0. That means when z equal to 0 plus I times 0 or 0, 0. So function itself is not defined. Other than that, for all points, it is valid. For all points in the domain, this function is valid. Okay. So this is the first question. Okay, this is from Fluid mechanics is a potential function and a stream function. No, these are conjugate harmonics. I'll just show this. Just now we did this, by the way. Just now we did this problem. In a different format, but still we will do this. So in fluid mechanics, the potential function and the stream function are, if I remember, they are conjugate harmonics. So let us do this. Dou phi by dou x is 2x, and dou phi by dou y is 2y. Okay, I don't remember the fluid mechanics part. It's more a question on fluid mechanics. Potential and stream function. I'll just get back to you on this. I'll have to refer. For those who are not from this discipline, that doesn't matter, but from fluid mechanics, potential and stream function, the derivative of the potential function is the stream function, if I'm not. Streamlines, and the tangent of the potential function is the stream. I'll have to see. I'll have to refer to that. Okay, next one. If potential function and stream function are functions expressed when, okay, this can be analytic if the Cauchy-Riemann equations are satisfied. Okay, the Cauchy-Riemann equations, and dou phi by dou y is equal to minus dou psi by dou x, and dou phi by dou x is equal to dou psi by dou y. So this is directly a question from mechanical engineering section. So it is directly based on this one. Okay, let us see this one, if this is valid. Dou v by dou y should be equal to 2x, which implies v will be 2xy plus a function of, I will not say phi now, some function of x. Now, differentiate with respect to x. This is 2y plus c dash x. This is equal to 2y, which implies c dash x equal to 0, which implies c of x is equal to a constant. Let's say k. So therefore, v will be 2xy plus k. But v means the psi function. But at x equal to 0, y equal to 0, the value is 0, which implies k equal to 0. So the function will be 2xy. So that's how we just applied the Cauchy-Riemann equation. Okay, why this one is coming? Okay, this one is direct. I'll not look into this. So many problems on Cauchy-Riemann equations. So now analytical function of a complex variable z is f of z equal to u plus iv. If u is given to be x comma y, what should be v? And it's an analytic function. So very simple. So dou u by dou x is equal to dou v by dou y, comma dou u by dou y is equal to minus dou v by dou x. So now dou u by dou x differentiating, we get y, and dou u by dou y, we get x. Now from Cauchy-Riemann equations, these are CR equations. Now from Cauchy-Riemann equations, dou v by dou y is dou u by dou x, which is equal to y, which implies integrating v should be y square upon 2 plus some function of x. Now dou v by dou x, differentiate this with respect to x. This term will be 0. We get c dash x. That should be equal to c dash x should be equal to minus of dou u by dou y. Minus of. So this will be minus of x. Okay, from Cauchy-Riemann equation. So which implies c of x will be minus x square upon 2 plus a constant. So v will be y square by 2 minus x square by 2 plus k. So y square minus x square upon 2 plus k. This is the answer. Again, so many similar problems said in different ways. Similar problems said in different ways, fifth and sixth. One function is given, find the other one. Generally, u is given, find v. So just we have to use Cauchy-Riemann equation. So in GATE, if you get this problem, if you know just the Cauchy-Riemann equations and analytical function, if you get a problem, you can easily solve it. It is hardly, it's a direct problem. So fifth and sixth are also of that type. So I'll leave that here. Now let's move to complex integration. I will introduce some topics of complex integration. Just a moment. Okay. Now, this is an important topic, by the way. And you get a lot of problems from this. So, first we define complex line integrals. We define complex line integrals. So, these are the definite integrals of a complex function. In complex plane, along a curve. Any curve between 2 points. This is complex line integral. These are just like, vector line integrals. Okay, vector integrals, line integrals where we discussed. So where C is the path of integration. Now, sometimes the curve C, now the path of C, the curve C can be parametrically represented like this. Instead of having two variables, C will have two variables, X and Y. So curve C, it's all Z follows this xt plus iyt. Okay, it follows some parameter in that sense. So if t keeps increasing, then it says that it's a positive sense of C. If t keeps decreasing, it is the negative sense of C. Okay. Now, if C is a closed path, then integral, the line integral is denoted as closed loop. So this is the basic definition of complex line integral. We will take some examples and solve. So properties of these line integrals. Properties of line integrals. First one is linearity. Linearity, that means integral C K1 F1 of Z plus K2 F2, two functions. Z will be K1 times integral F1 of Z plus K2 times integral F2 of Z. So this is the linearity property, so which is followed for just like real integrals. Then sense reversal is another property. See, along the same path, if from Z1 to Z2 we are integrating function, that will be minus of Z2 to Z1 along the same path. So in a complex plane, let's say whatever the path is, this is Z1, this is Z2. Okay. Next, partitioning. Integral Z1 to Z2 f of z dz is integral Z1 to Z naught f of z dz plus integral Z0 to Z2 f of z dz. So this we know. So suppose this is the path Z1, Z2, this is Z0. So if there is a partitioning of the path, this integral can be evaluated like this. In the previous case, if we are going from Z1 to Z2 and we are coming from Z2 to Z1, the integral will change the sign by -1. So these are the three properties. Now, methods of integration. So the first method, is using indefinite integrals of analytic functions. That is, if we have integral Z0 to Z1 f of z dz will be capital F of Z1 minus capital F of Z0, where F dash Z is equal to F of Z. That means capital F is the antiderivative of small f, or F is the derivative of capital F. Okay. Now, only requirement in this case, only requirement is that f of z must be analytic. Just like in real functions, we had that it should be differentiable. Now, this must be analytic in simply connected domain. And Z0 and Z1 are in the domain. It's a simply connected means we from Z0 to Z1, any path you choose, they are all within D. So this is the requirement for this integration to happen. So let's take example. Integral 0 to 1 plus I z square dz. That means from 0 comma 0 to 1 comma 1 we are integrating. Now straight away the integral is z cube upon 3 from 0 to 1 plus I. So 1 plus I the whole cube minus 0 cube upon 3. So we get 1 plus 3I square plus 3I, okay, plus I cube. So this is minus 1 minus 3, that is minus 2. And this will be I cube will be I square into I minus I. So 3I minus I is 2I. So you get this minus 2 by 3 plus 2 by 3I. This is the integral value. Let's look at the second example. Now integral minus I to I dz by z. Okay, now this will be path independent. This will be path independent. Only thing is we should not cross 0. The minute it crosses 0, this function will not be defined. Otherwise, for all other purposes, this will be log z from, minus I to I. So what will be log of I? So this is log of z. I minus I is e power minus pi by 2 times I, and this is e power pi by 2 times I. So you get log e power I pi by 2 minus log e power minus I pi by 2. So this is I pi by 2 minus of minus I pi by 2. So plus we get I times pi. I times pi. So this is the first method of integration. Just directly apply the antiderivative and substitute. Now, second derivative, a second method is using the path of integration. Integration by using the path. This we will use very commonly. Now, to evaluate integral f of z dz, along a path C. So we have these following steps. So first step is represent path C in the form of a parameter. And this parameter may vary from A to B. Okay. Next, calculate, find dz by dt and then substitute z by z of t, then evaluate this integral. This becomes integral f of z is replaced by the parameter and dz is replaced by dz by dt times dt, and t varies from A to B. By evaluating this, you can find this integral. Now we will discuss two most important integrals in complex analysis. Very fundamental and important, very important examples. The first one, evaluate integral the closed integral over C of 1 by z dz, where C is a unit circle. C is a unit circle with center at z equal to 0. So remember that at z equal to 0, this function is not defined. The function is not analytic. So now we have to evaluate so this is the z plane. I'm not talking about the 1 by z w plane. So this point is 1 by z is not analytic. 1 by z is not defined. So it is not analytic point. And now we find a unit circle. Okay. And our path of integration is a closed loop here. Integration path. So this is an important problem. Now let us see how we can uh, solve this. So let C be Z of t is equal to hmm, e power I e power it. This is the path because modulus of this is 1, and if t takes values from 0 to 2 pi, or minus pi to pi, okay, 0 to 2 pi, then it completes the loop. All right, so now let us find dz by dt, which is e power it into derivative of it, that is I. Now let us do this. Integral is integral. Now the path is 0 to 2 pi. 1 by z is 1 over e power it times dz by dt times dt. So integral 0 to 2 pi 1 over e power it into dz by dt is I e power it dt. So we get integral 0 to 2 pi I dt. This is 2 pi I. Very important result. Extremely important result. So along a unit circle, integral of 1 over z is 2 pi I. Next example. Example 2. Now if f of z is z minus z naught whole power m, then evaluate integral f of z dz if C is a circle of radius r and having center at z naught. So now we have to choose the path. Now we have to choose a path. This is real z, imaginary z. Now this is the point z naught. Okay, I'll first draw the shape. And then put the center. Now I need to integrate over this path. So how will I write this path parametrically? The circle C can be parametrically written as how? How can we write? Now, the distance from this is R. Now, Z is any point here. So, Z minus Z naught is R into e power it. This will be the path. So, Z of t, this path C, Z of t is Z naught plus R e power it. R e power it. Okay. So how is this? Because Z minus Z naught modulus gives R, and as t keeps changing and t varies from 0 to 2 pi, you get all the points here. So now let us integrate this. So this is Z. Now let us find dz by dt is R I e power it. Now we want to evaluate this integral C Z minus Z naught whole power m dz. Now Z minus Z naught, if we replace, now t equal to 0 to 2 pi. Now Z minus Z naught will be replaced by R e power it whole power m, and dz by dt is R I e power it. So we get integral 0 to 2 pi R power I comes out R power m plus 1 into e power it to the power m plus 1. So now we are integrating with respect to t. So I R power m plus 1. All right. This you get e power I m plus 1 times t by the coefficient I m plus 1 from 0 to 2 pi. Now this has an issue. This is as long as m is not equal to 1. If m is not equal to minus 1. If m is not equal to minus 1, we substitute this. We get I R power m plus 1. Now e power any multiple of 2 pi cos. So e power I m plus 1 times 2 pi minus e power I times 0. I cancels anyway. Now r power m plus 1, no matter what the r power m plus 1 by m plus 1 times cos 2 pi is 1 plus I sine 0 minus 1 minus I 0. So 1 minus 1 is 0. So we get that this integral is 0 if m is not equal to -1. Now comes a very important result. If m were to be -1, then what happens at this level? Then I will start from here. Integral 0 to 2 pi I times r power m plus 1 into e power I m plus 1 times t dt. Because m plus 1 is 0, we get r power 0 and e power 0. I dt. So you get 2 pi I. So again, a very important result. If, what is this? If m equal to -1, if m equal to -1, then this is integral 1 by z minus z naught dz. Now, this is over this closed path C. What is, I'll just do that. So this is z minus, this is z naught. And we are taking a unit circle around it. We are taking a unit circle around it, around z equal to z naught. Now, z equal to z naught is a point where the function is not analytic, function is not defined. So 1 by z minus z naught dz is equal to integral 2 pi I. Just look at the previous one. Integral 1 by z dz equal to 2 pi I when this path had the center at origin. So whenever there is a point of non-analyticity, that means function is not defined and function is of the form 1 by z minus z naught. And you take a path, a circular path around z naught, okay, with center at z naught, you get the integral as 2 pi I. And note, very important note, that this is independent of the radius. No matter how big the radius you choose, this r, this path had the radius r. So this is irrespective of radius r. Okay. So this will also be irrespective of radius r. You can see here. Of course, we did a unit circle. Even if it was r, r and r would have got cancelled. So what we understand is, if there is a point of non-analyticity and you integrate 1 by z minus z naught around that point of non-analyticity, that is z naught, around a circular part, the value of the integration is 2 pi I. So this is very fundamental. All right. So we'll stop here. I will take a class on Tuesday and if possible on Thursday. We'll cover complex integrations within those 2 days. I'll take 1 hour on Tuesday and Thursday. All right. I